Okay, so this is our next video covering material from section 4.4 in the textbook for Math 1560 Calculus 1 at U of L for fall 2017. And in this video we're going to introduce the concept of a differential. So differentials are very closely related to the linear approximations that we talked about in the previous video, right? So in the last video we said if you've got a differentiable function, then at any point where the derivative exists you have this linear approximation, also called the linearization, right? So L here is this is your linear function, right? Remember that these are just constants. So this is really, it looks like something like, so this is like your b, this is your slope, right? So it is very much a linear function here. All right, if you were to graph this thing, you get a straight line. That line that you get is the tangent to the curve y equals f of x when x equals a. And so we talked about how this linear approximation, as long as you don't go too far away from this point a, it gives you a good approximation to the original function. So one of the things that you look at here is you look at what happens to both the original function and the linearization if you move a little bit away from a, right? We're kind of interested in, what's the error? What's the difference between the kind of the actual change in the function and the one that we get using the linear approximation? And so if you do a small change in x, right, and you look at what happens to the original function, well then we calculate, so this is our, if you like, you can think of this as delta y. Right, so delta y is f at the new value minus f at the old value. You could also consider the change if instead of following the graph of f you just moved along the tangent line. So we stay on the tangent and we see what happens. And this quantity here, for reasons, well, I don't know, historical reasons, I'm not sure why we call it dy, but we'll try and flesh out this notation in the next slides. The change along the tangent line is often referred to as dy to distinguish it from the delta y that you get if you stick to the curve. And so if you calculate the value, calculate the linearization at a plus delta x, so you plug a plus delta x in, right? So if you plug this number in up here for this x value, right? And well, we notice that a plus delta x minus a is just delta x, right? So that gives me the f prime of a times delta x. We're adding that f of a. What do we get when L is equal to a? Well, or so at L of a, right? When x equals a, well, when x equals a, this is just 0. So L of a is just f of a. So there's L of a. It's also f of a. That makes sense, right? The original graph and the tangent line agree at that point, right? That's the point where they intersect. So we just get this. We just get the derivative times the change in x, right? So that's the change that we get if we stick to the tangent line. So the definition of the derivative gives us this approximation, right? So we get that delta f is approximately delta y, delta L, sorry, or in terms of y, delta y is approximately dy. Okay. So this is this approximation idea that we're going for, and for reasons that well, we'll try to spell this out a little bit, but this dy, so dy is given by f prime of a times delta x, and we often equate delta x with dx, and so we get this f prime of a times dx, right? And so we use d for linear changes. I mean, x is a linear function of itself, and so dx, delta x, they basically mean the same thing because the function just y equals x. It's already linear. That's essentially the idea here. So this is what's called, this is an example of what's called a differential. Okay. So the notation is this. If we have the differential, and so this again is also sometimes called dy, if we're looking at the graph y equals f of x. So df or dy is f prime of x times dx. We'll see that these differentials are going to come in handy at the very end of the course when we talk about substitution in multiple integrals, where we want to define one variable in terms of another, and it's going to be important to know how these differentials are related when we're doing integration. So we're going to see a little bit of that later on. So we view dx as interchangeable with delta x. We mentioned that on the previous slide. And in a sense, this df or this dy, right, it really depends on a, right? Dx is representing some small change, but the change in y, the little change in y that we get by making a change in x, right, it also depends on what point we're at. It depends on the value of x. And so we could kind of use this functional notation here and think of df as depending on this point A, but you usually don't see this. Usually there's a context that kind of tells you what point you're looking at. Occasionally you may see this though. Okay. So basically what you want to think of here is you can think of whatever function you're dealing with, and we'll think about this pretty soon. We're going to talk about polynomial approximations in the next section. So we can think about a complicated function as having kind of a a linear part and then a quadratic part and then also maybe some higher order things. And if we change x, then each of those parts is going to change. The differential is telling you how the linear part of your function changes, right? And ignoring all the higher order stuff, because if x is really, really small, all that higher order stuff is hopefully negligible. Okay, so this is our approximation. In certain cases, you might talk about the error, the difference between delta f and df, and you can argue that that error is going to be small if you're dealing with a differentiable function. Okay, so just some basic examples. Let's say we're dealing with something like f of x equals sine x, right? So df or dy, if you like, is going to be cos x dx, right? If we were dealing with let's say we're dealing with y is equal to something like 3x plus 5x squared minus x cubed, then our dy is going to be 3 plus 10x minus 3x squared times dx, and so on. And then what we could do is if we were, let's say we're looking at this last one, if we were near, let's say we're near, I don't know, x equals 1. So if x equals 1, then y is going to be what? 3 plus 5 minus 1, y is equal to 7, right? Then your dy is going to be 3 plus 10 minus 3. dy is going to be 10 dx. Right? So what does this mean? This means that a small change in x produces a small change in y, but it's going to be 10 times as big, right? So dy is 10 times dx, meaning that if I change dx by 0.1, then dy should change by 1, right? And in fact, let's think about what would happen if we did that, right? So let's say we go from x equals, so let's say we go to 1.1, so dx is 0.1. So this is going to be our change, right? So we change to 1.1. dx is now 0.1. So then we get that dy is going to be 10 times 0.1, which is 1. So we expect that changing x by 0.1 here should change y by 1. And so then if we wanted to get our delta y, right, for delta y, we would have to calculate 3 times 1.1 plus 5 times 1.1 squared minus 1.1 cubed. And we'd have to work out what that is. And that's going to be a little bit messier, right? This is going to be what, 3.3, 1.1 squared is 1.21. Then we have to multiply by 5, so we get like 1.21, and we multiply by 5, right? So that's going to be 6.05. And then we would subtract 1.1 cubed, whatever that is. Actually, let's bring out our calculator again. 1.1. Oops. Clear that. 1.1 cube it. Oh, 1.11. Hang on. That's better. Cubed. 1.331. Okay. Let me make sure I didn't mess up that other one. 1.33, so 1.1, we square it, times 5. I did mess that one up. No, there it is. 6.05. Oh, it multiplied by 5 twice. Okay, 6.05. Okay. All right. 1.331. Okay, so let's see what that gets me. 3.3 plus 6.05 minus 1.331, 8.019. Okay, minus, well, okay, so this is, we got to do this, subtract the 3 plus 5 minus 1, right? Delta y. So it's y at, oops, 3 times 1. So we're doing delta y. So it's y at 1.1 minus y at 1. And so we've got to subtract 7, and that gives me 1.019. So a delta y of 1, that's a pretty good approximation, right? That's a pretty small error in using the linearization to approximate the change in y versus calculating the actual change in y. So you can see why these approximations are useful, right? Calculating dy was a whole lot easier than calculating delta y. I didn't need a calculator to do it. Okay. Now, you can stop here if you're not worried about this whole dx equals delta x thing. If you're really wondering why we make this identification, well, if you think about starting with a linear function, right? A linear function it's already a linear. So if you were going to approximate a linear function by a linear function, what should you use? You should use the same linear function, right? If you draw the tangent line to a line at any point, it's the same line, right? So we notice that here. You can actually formally calculate this, and you can confirm that at any point, the linearization of a linear function at that point gives you the original function. And so what we were saying is that normally what we do is delta f, is approximated by df, but actually here delta f equals df, right? Because nothing happens when we linearize. And so in particular, if you take the function which is just f of x equals x, then we can see that you do in fact get that delta x equals dx. And so this is why, although dy and delta y are not the same thing, if y is given by some nonlinear function of x, dx and delta x can be viewed as exactly the same thing because, well, x depends linearly on itself. Alright, so we're going to do one more video on differentials. We're going to talk about how to use them to calculate error in the next video.